Absolutely on the first page, on the top, the heading Laws of Thermodynamics and their Relevance in the Biological System. So I had given you a video before of a previous class. Please go through that video. I've talked about some things extra over there too. You can go through that video and lectures. And those are my old videos. You can go through it. But today's class, I'll just go from a note which you actually have to study in your exams. This should be good enough. So what do you mean by thermodynamics? Basically, thermodynamics, as the name suggests, thermo means heat, dynamics means movement of heat. So this heat can also be translated into energy. So in the biological system, this transfer of energy is extremely important. You have first from the sunlight, take carbon dioxide from the atmosphere, then you take minerals from the soil, and then what you do is you make energy in the form of food molecules called glucose through the process of photosynthesis. And now energy from the sunlight has been transferred into the food, into sugars, and now those are eaten by the the first herbivores, primary herbivores, the first heterotrophs. They take that energy, they concentrate that energy, and they make their muscles and all, which is also energy. They are eaten by the secondary herbivore, the carnivores, or you call. And so these carnivores, they take the energy from the herbivores. Then you have the secondary carnivores, those who feed on the carnivores also. They also take the, so energy is being transferred in each step. There is always a loss of energy. Gain of energy is only from the sun. So in one organism loses and the other gains. Right. So this is how the biological system works. This is the basics of thermodynamics. One law of thermodynamics states that energy can neither be created nor destroyed. It just changes forms. Einstein also, via his theory of relativity, he said that matter and energy can be converted. So basically, nothing is lost in this system. The sum total of the energy remains the same in the system. It doesn't go away. System in the universe, it's the same. The sum total of all the energy will always remain the same. You may lose energy at one point, but you will gain energy at another point. So this is how is it. So, biological thermodynamics. It is the quantitative study. So there is some numbers involved. You do it quantitatively. How much energy is gained and how much energy is lost. So of energy transduction. Transduction means movement from one place to another place. It's transmitted from one place to another place. That occur in between living organisms, structures, cells, and the nature and the function of the chemical processes underlying these transductions. So basically, between organisms, in biological terms, between organisms, what energy you release to the environment, to be in nature outside, or what energy you give to other organisms to feed on you. So biological thermodynamics, it addresses the question whether the benefit associated with any particular phenotypic trait is worth the investment it requires. Now in biology, there is a energy benefit ratio which has been taken. The cost benefit ratio is always calculated by an organism. It's through nature, an organism always tries to profit. It has to spend something to benefit something. So you have to pay a price to get something. So what you do is you have to evaluate whether the cost is good, is sufficient or good enough that I get better benefits. So if anybody says that apart from human beings, any organisms living organism, they don't look for profit, they are wrong. Maybe they don't look for monetary profit, but all organisms try to look for profit. In some places, in some social science seminar, I was talking, I heard this term a lot, and I questioned them that why do you say that human beings only care for profit? They don't care about the environment. Nobody cares about the environment. If monkeys had sufficient intelligence, they would have also destroyed the environment. The cycle would have gone. But if we destroy the environment, it will ultimately harm our survival itself. You cannot directly say. So transfer of energy is taking place from organisms. So from one step to another step, there is some loss of energy to the environment. That loss may be in the form of heat, your body temperature. You're losing that energy which is being generated inside. So the next thing is we are talking about the focus of thermodynamics in biology. So it is based on the principles of chemical thermodynamics. You have the three laws of thermodynamics, where energy can neither be created nor destroyed. When it go, entropy of the universe cannot be created nor destroyed. The entropy remains constant. So energy increases the entropy, and then you have one thing known as the Gibbs free energy. Gibbs free energy is an internal energy present in an organism or in a molecule. Every molecule in this world has got some energy present inside it. That is known as free energy. Now, when a chemical reaction takes place, a substrate is getting converted to a product. So while this product is taking place, there are two types of reaction. One is one reaction which takes in heat or takes in energy, and one which releases energy. So a molecule is at a gradient, at a level of energy, internal energy, that is the Gibbs energy, free energy. And now when it is getting converted into product, it may gain energy. You have to give some energy to make a product which has got a higher energy than the substrate, or that substrate breaks down and releases some energy, and it goes the product is at a lower energy state than that of higher energy, okay, of the substrate. So this is known as the Gibbs free energy change. Every reaction takes place. Why does a reaction take place? A reaction takes place is when that substrate has got higher energy, it wants to release energy and go to a lower energy state. That is the normal gradient of energy flow. But for example, if you keep petrol, all you need is a bit of energy known as activation energy. Just a little spark, that petrol will catch fire and it will form carbon dioxide. It will burn and form carbon dioxide. So that carbon is getting converted into carbon dioxide. You need a little bit of energy which you have to give. Even though that reaction is it releases this fire. When it catches fire, it releases heat. But still, it needs a little bit of an activation energy. So therefore, if you keep something for a longer time, automatically it doesn't change into for some time it doesn't change into a product. That is the reason why if you keep this pen for 1 day or 2 days, it will not get destroyed. But if you keep this pen for 100,000 years, you will see it starts to get destroyed. So this is how a reaction proceeds. You need to give a bit of an energy that is known as activation energy. Although the product will be at a lower activation energy state, lower free energy state. So this is one of the basics of thermodynamics. So principles are the first law of thermodynamics. The second law of thermodynamics gives free energy, statistical thermodynamics, and reaction kinetics. So these have been used to hypothesize the origin of life. So in any biological reaction which takes place, who gives the energy to raise it at a higher potential? In glycolysis, glucose gets converted into glucose 6-phosphate. The enzyme is hexokinase. So glucose is at a lower energy state. Glucose 6 phosphate is at a higher energy state. And where the energy comes, it comes from ATP hydrolysis. ATP hydrolyzes and transfers that energy to the glucose molecule. It becomes glucose 6 phosphate. That's a high energy phosphate. In my next lecture, I'll talk about these high energy phosphates. And I've told what is Gibbs free energy. It is the energy which is present in a molecule. It can be high, it can be low. The next thing which you need to study is energy transformation in biological system. The sun is the primary source of energy. In this universe, no sun, no energy. Well, from inside the earth also you can get some energy. But for life, the sun is the energy source for life. So organisms like plants, they need sunlight. And humans, they eat that plant and get this energy. So this is energy flow. So the relationship of energy of the incoming sunlight and its wavelength is lambda. And its frequency, wavelength is distance between two troughs or two peaks. That is a wavelength. Wavelength small means shorter wavelength. It's much shorter. Wavelength long means longer wavelength. Visible light has got from 300 nanometers to 700 nanometers. 300 nanometers violet light, 700 nanometers is red light. Any shorter wavelength is ultraviolet. Longer than red, it is infrared. And our mobile and radio waves, they are very, very long waves. Maybe it starts from here and it goes to the after that tree, maybe the wave falls. Those are very long wavelengths. So if people say that mobile waves and radio waves are harmful, they are wrong. It is not harmful. It is even your visible light is more harmful than your mobile wave range. But what is bad about this mobile phone is the battery. Especially when the charge is low, it releases electrons. Electrons have a very short wave. Electrons are released and those have got short waves. Shorter wave means higher energy, longer wave means lower energy. So it is given energy is equal to hc by lambda. H is the Planck's constant and c is the speed of light, 3 into 10 to the power 8 meters per second. So plants trap this energy and via photosynthesis they synthesize chemical energy in the form of food. Now let us talk about the first law of thermodynamics. It is the law of conservation of energy. Energy cannot be created nor destroyed. It can be changed from one form to another. লিখতে হবে না, এই তো বলি এটার মধ্যেই এটা করতে। It can be changed from one form to another. Energy can neither be created nor destroyed. Clear? From the first law, there is another law which can be done. That is known as Hess's law. It states that the heat absorbed or given, heat which is taken from environment or given in a particular reaction must always be constant and independent of the manner in which the reaction takes place. So that means if the substrate molecule is at x energy level, whether the product is at the y energy level, which is lower, whether you give an enzyme, what does energy do? What does an enzyme do? It reduces the activation energy needed. So that initial activation bump, which is higher, that is lowered by the enzyme. So even if you use a enzyme, the substrate energy, product energy, it should be however the reaction takes place, whether you give it an enzyme or whether you don't give it an enzyme, it remains, it will be the same. Product energy will be the same. It will have this much amount of energy, and substrate will also have this much amount of energy. Although some intermediate reactions may be endothermic and others may be exothermic, the total heat exchange is equal to the heat exchange which had happened with the process directly. So this enzyme thing which I just talked about. This is the principle for calorimeter, which is used to determine the amount of heat in a chemical reaction. Now we go to the second law of thermodynamics. So this is concerned whether or not a given process is possible or not. Will this particular process take place or not? Will this particular reaction take place or not? Yeah. Will it take place or not? So this is actually this thermodynamics says. So it says that no natural process can occur unless it is accompanied by an increase in the entropy of the universe. Entropy is randomness, chaos. In ice, the molecules are fixed. Then as it becomes water, the molecules move about. So water flows like this. Then it becomes gas. It's so volatile, so much energy that it starts to float in the atmosphere. Clear? So this is, so there is a reaction of, if you keep an ice over here, the reaction is that it will, there will be an increase in entropy. The molecules of water will start moving, that ice will become water, and that water will become vapor. It will evaporate as vapor. Okay. If you state it differently, an isolated system. Isolated means there is no exchange from the system and its environment. It is closed. In an isolated system, will always tend to disorder. Living organisms mistakenly believe to defy the second law of because they are able to increase their level of organization. But one must simply refer to the definition of the system and boundaries. What is the boundary? A living system is an open system. We are always giving up this energy to the environment. So, if I have an X amount, if the glass has got an X amount of disorder or chaos, entropy, it tends, it is flowing into the herbivore. So the herbivore, in between, it is not getting the complete energy. Some of it is lost in an open system in the atmosphere. Some energy is lost. Completely it's not transferred. So therefore you will say that I have taken 10 kilocalories of food, but why have I got 9 kilocalories only? Because that 1 kilocalorie has been given to the environment. That's an open system. But in a closed system, it will not be lost. There is no closed system in this, theoretically no closed system. Now we go to Gibbs free energy. Energy and entropy change together. Higher energy, more entropy. জল ফোটালে টকবক টকবক করছে, ঠিক আছে? So you don't have to look at this derivation. If you are interested, I can give you the derivation. But this formula G is equal to H minus Ts. H is the enthalpy, the internal heat present inside an organism, internal energy present in a molecule. T is the temperature. S is the entropy. Entropy is randomness. Joule per Kelvin, energy movement per degree rise in temperature. At 4 degrees, ice becomes water. ठीक है, ice starts to become melting point. And entropy बढ़ रहा है. At 5 degrees, it increases more. At 100 degrees, it starts to boil, becomes vapor. So, and Gibbs free energy change, I told you, product minus substrate is the Gibbs free energy. When it is negative, it means energy is released. Product minus energy in product minus energy in substrate, that is delta G. If it's negative, then energy is released. If it's positive, energy is taken. Okay, ATP, the example of ATP. I've already given this glucose 1,6-phosphate example. So this is what you study in thermodynamics. And bioenergetics is a reaction, for example, glucose to glucose 6-phosphate. It is normally not feasible. Okay, it is only feasible when another reaction is linked. That is, ATP is broken into ADP plus PPI and energy is released. That energy raises glucose to a higher energy glucose 1-phosphate. Then again another ATP is taken, becomes glucose 1,6-phosphate. So at these reactions, they are taking energy, but energy is lost from ATP. So both exothermic and exergonic and endergonic reactions, they take place together in biological system. So all biochemical reactions are metabolically coupled. ATP hydrolysis happens, that happens because of a small change in energy. Activation energy is given. There is an enzyme which lowers that activation energy. ATP hydrolysis takes place. And the hexokinase energy enzyme does that. It breaks that ATP, and that energy is transferred inside the molecule into inside the enzyme molecule into the glucose molecule, and it becomes higher energy molecule. Growth, development, living organism, autotrophs, then respiration, all of these include any biological process requires the laws of thermodynamics to work. And this is end of this chapter. Okay, so I finish my class here, and next day we will talk about high energy phosphates. I've already sent the note and the video also. Go through the video, see the notes, and then come to the class. It will be easier for you to understand. Okay, sir? Do you people have any questions? No questions?